Hello, here's a video covering Chapter 4 test review. This is a good overview of what you've learned in Chapter 4. So the first question is, find all extrema for the function f of x equals 2x squared minus 2x plus 3 with a domain of 0 to 3. So to find extrema, we're going to look for stationary, singular, and endpoints. These will give us the possible candidates for the extrema. So for the stationary points, you take the derivative, set equal to 0. So the derivative of 2x squared is 4x. The derivative of negative 2x is negative 2. The derivative of 3 is 0. So we take 4x minus 2, set equal to 0. Solve for x. So we add 2 to both sides, which leaves us with 4x equals 2. Divide both sides by 4. We get x equals 1/2. Then for the singular point, we look at the derivative and see if there's any place that makes it undefined. So it'd be like dividing by an x, or where an x is in the denominator. In this case, we have 4x minus 2, so there are no singular points. And then endpoints come from domain. So domain is given at 0 to 3. So our possible points are 1/2, 0, and 3. So we can make a table of 1/2, 0, and 3. We take 1/2, plug into the original function, and it gets us 2.5. We plug 0 into the original function, gives us 3, and plug 3 into the original function, and it gives us 15. So then we're going to look at those points to see if we have an absolute max, or a minimum, or a relative max or minimum, or local max or minimum. So we graph it. So the domain is 0 to 3, so our x-axis will go from 0 to 3. And then for our y-axis, we look at the f of x, and the lowest is 2.5, the highest is 15, so I did a window from 0 to 20. We graph the original function, and then we can look at each point. So the first point, 1/2, 2.5, 1/2, 2.5, that is going to be a minimum, and it's the lowest point in the entire graph, so we have an absolute minimum. The next point is 0, 3, so 0, 3 is also, so the first one's an absolute minimum. And then we have 0, 3, that's a maximum, but it's not the highest point in the entire graph, so that would be a relative or local max. Then we look at the last point, which is 315, and 315 is a maximum, and it is the highest point in the entire graph, so we have an absolute max. So again, 1/2, 2.5 is an absolute minimum. 0, 3 is a, let's say, local max, and 315 would be an absolute max. Okay, for our next example, we have find all the extrema for the function f of x equals 1/x plus 2x with a domain of negative 3 to 3. We're going to go through the same steps, stationary, singular, endpoints, but first step I'd rewrite the original, so instead of 1/x, we write x to the negative 1 plus 2x. And then we do stationary, take the derivative. The derivative of x to the negative 1 is negative 1 x to the negative 2. The derivative of 2x is 2. So we have the first derivative is negative 1 x to the negative 2 plus 2 equals 0. Then we're going to solve for x. This will take a little bit of algebra. So I'm going to rewrite, instead of negative 1 over x to the negative 1 times x to the negative 2, we have negative 1 over x squared plus 2 equals 0. And one way to solve this is set up a proportion. So I'm going to add 1/x squared to both sides, which gives us 2 equals 1/x squared. Now that we have a proportion, we can solve the proportion by cross multiplying, which gives us 2x squared equals 1. To get x squared by itself, we divide both sides by 2, which gives us x squared equals 1/2. And to turn x squared into x, we take the square root of both sides, which gives us x equals plus or minus square root of 1/2. Square root of 1/2 is 0.707, so we have x equals plus or minus 0.707. For singular points, we look at the derivative, negative 1/x squared plus 2, and a number that would make this undefined would be 0, so we have a possible singular point at 0. And endpoints come from the domain. The domain is negative 3 to 3, negative 3 and 3. So we take our points that we found and make a table. So we have negative 0.707, plug it into the original function, we get negative 2.83. Take 0.707, plug into the original function, we get 2.83. Plug in 0 into the original function, we get error undefined, which means that it won't be an extrema. And we'll talk about what is there. If we plug in negative 3 into the original function, we get negative 6.33. Plug in 3 into the original function, we get 6.33. Now we're going to graph the original function and see what we have. So our domain is negative 3 to 3, so that's our x-axis, starting at negative 3, going to 3. To determine our y, we're going to find the lowest is negative 6.33, and our highest is 6.33. So I used a window of negative 10 to 10. So as we look at each point, we'll identify what it is. So at negative 0.707, comma negative 2.83, we have a maximum, but it's not the highest point in the entire graph, so that would be a local max. At 0.707, comma 2.83, we have a minimum, but it's not the lowest point in the entire graph, so we have a local minimum. The next point we're going to check is 0. Notice 0 is undefined, but you'll see that we have a vertical asymptote at 0. If we look at negative 3, comma negative 6.33, and 3, comma 6.33, at negative 3, we have a minimum, but since this graph goes down forever, it is not an absolute minimum, it would be a local minimum. And at 3, we have a maximum, but it's not the highest point because the graph goes up forever, so it would be a local maximum. So again, at negative 0.707, comma negative 2.83, we have a local max. 0.707, comma 283, we have a local min. Neither on 0, negative 3, comma negative 6.33, we have a local min, and 3, comma 6.33, we have a local max. Okay. Number 3 is a word problem. The consumer demand for tissues is given by Q equals 100 minus P squared, where P is between 0 and 100, including 0 and 100. P is the price per case of tissues, and Q is the demand. So we're given demand, but the question asks for revenue. So to turn demand into revenue, we take demand, Q, times P. So P times 100 minus P squared, we simplify. 100 minus P squared is 100 minus P times 100 minus P, simplify, multiply by P, and we get our revenue function, 10,000p minus 200p squared plus p cubed. Now we're going to go through our steps, stationary singular endpoints, but we'll use the graph, which our domain is from 0 to 100, and then the y is given from 0 to 200,000, but we can get that from our table. So we do stationary singular endpoints. So for stationary, we take the derivative. The derivative would be 10,000 minus 400p plus 3p squared. Since it's quadratic, we can use quadratic formula. A is positive 3, B is negative 400, C is 10,000, and we get two answers. P equals 33.33, P equals 100. The derivative, there's no place it's undefined for price, so there'll be no singular points, and endpoints were given at 0 and 100. So the 3 points we're going to look at is 33.33, 0, and 100. When you take 33.33 and plug it into the original revenue function, you get 148,148. 0 price into the revenue function, you get 0. 100 into the revenue function, you get 0. So it becomes pretty obvious that the answer will be to maximize revenue, you would charge 33.33. That is verified in the graph. There's your absolute maximum at 33.33, and your revenue at that point is 148,148. Question 4. We would like to maximize area of a rectangular enclosure giving the following equations. So area is x times y. We're trying to maximize area, but we have x times y, two variables. So we have to have a given. The given is x plus 2y equals 40. So again, the problem is we can't maximize x times y because we have two variables. So we use the given, x plus 2y equals 40, to substitute into what we're trying to maximize. So we're dealing with one variable. So we have x plus 2y equals 40. So it's easier to solve for x, so we subtract 2y from both sides. So we have x equals 40 minus 2y. We take the x equals 40 minus 2y, plug it in for x, and that will give us area equals, instead of x, 40 minus 2y times y. Distribute the y. We have area equals 40y minus 2y squared. Again, now we're dealing with just y's instead of before x and y's. And we go through our stationary singular endpoints. So for stationary, we take the derivative. Derivative of 40y is 40. Derivative of negative 2y squared is negative 4y, set equal to 0. So we add 4y to both sides. 40 equals 4y. Divide 4 by both sides. We get y equals 10. There are no singular points, and there were no endpoints given, so y equals 10. To find x now, we can use x equals 40 minus 2y, plug 10 in for y, and that will give us x. So 40 minus 2 times y equals 10, x equals 20. Now that we have x and y, x is 20, y is 10. The area is 20 times 10, which is 200. Therefore, x is 20 units, y is 10 units, and the area would be 200 units squared. Number 5. The cost function for the manufacturer of portable music players is given by C of x equals 150,000 plus 20x plus 1 over 10,000 x squared, where x is the number of music players to be manufactured. But we're not looking to minimize cost, we're looking for average cost. So to turn cost into average cost, you take the cost, 150,000 plus 20x plus 1 over 10,000 x squared, divided by x. 150,000 divided by x is 150,000 over x. 20x over x leaves you with 20, and 1 over 10,000 x squared over x, x's cancel, so you get 1x cancel, so you get 1 over 10,000 x. That can be rewritten as the average cost equals 150,000 x to the negative 1 plus 20 plus 1 over 10,000 x. So now we go through stationary singular endpoints to minimize average cost. So if we want to take the derivative of 150,000 x to the negative 1 would be negative 150,000 x to the negative 2. Derivative of 20 is 0. Derivative of 1 over 10,000 x is 1 over 10,000. Set it equal to 0 and solve. Negative 150,000 x to the negative 2 can be written as negative 150,000 over x squared plus 1 over 10,000 equals 0. And doing some algebra, we can set up a proportion. So we add 150,000 over x squared to both sides, which gives us 1 over 10,000 equals 150,000 over x squared. Cross multiply. 1 times x squared gives you x squared. Then we do 10,000 times 150,000, which gives us 1,500,000,000. But we don't want x squared, we want x, so we square root both sides. So we have x equals plus or minus 38,729.83. But remember, the domain says that, well, we can't deal with a negative in this problem, so a number of players. So the only answer that makes sense is 38,729.83. Plug that into the original, and we get an average cost of 27.75. So to explain that, to minimize average cost, you should produce 38,730 players for an average cost of $27.75 per player, and you can actually make a graph of this to verify that answer.